Hello everyone and welcome to our Natural Intelligence Architecture webinar. I'm Ohad Israeli, a platform architect at Natural Intelligence, and with me Aviem, our data architect. At the session today, we will give you an overview of the NI architecture, serving and data platform. We will list some of our guidelines principles for designing system architecture and have a look at our data architecture. If you have any comments or directions to other areas that you would like us to speak about in this meeting or any following meetings, please let us know. In order not to interrupt the presentation flow, please use the chat or Q&A tab in order to ask your questions, and we promise to answer them during the presentation or by the end of the presentation. So now we are ready to start. This session is all about natural intelligence architecture. But wait a second. I'm not sure that all of you know what we are actually doing in the company. So let's have a few slides explaining our use case from the user perspective, a user who is currently using the system. So meet Joe. Joe is a senior citizen who lives in Florida, Orlando, and lives a peaceful life. But sadly, someone broke into Joe's apartment yesterday. The burglar was lucky that Joe hadn't been at the apartment at the time, but sadly the burglar turned Joe's apartment upside down. It's all because Joe didn't have a security system installed in his apartment. So after calling the police and during the initial cleanup, Joe found out that the burglars forgot to take one of his laptops. And he also noticed that the internet router is still in his place. So Joe immediately started looking around in order to figure out which alarm system to purchase. Joe Googled the term top home security system and got several responses to his search. Behind the scene, if you don't know, there is a bit battle between several candidates on the keywords that Joe was using in his search. It seems that we didn't have a high enough bid, as some other partners took the first and second place and we got only to the third place in the list. But luckily enough, the description that we added there was pretty attractive to Joe, and he decided to click on our Google ad. And with a click of a button, Joe found himself being redirected to one of our umbrella sites, a site by the name of Top 10, which holds a large amount of verticals comparing various products. These sites allows Joe to make smart decisions about product or services that he would like to purchase. We also have sites dedicated to fintech industry, gaming industry, and more. So within Top 10, Joe arrived to a page ranking the best home security systems in the market. And this is what we would like to give you an overview on. Let's take a look at our serving and back office architecture, and later on dive into our data architecture. We'll start with a high-level overview of our system. If you look at our system for 30,000 feet above, you can spot several domains which bring us to the essence of NI, Natural Intelligence. Natural Intelligence is a sophisticated CMS engine with state-of-the-art rule engine and testing engine. Our system allows us to serve the same page as Joe was redirected to in multiple permutations. Based on statistical metrics and models, we can match the user with the best comparison page, which allows him to take decision in an area of his choice. Let's take a look at the diagram in more details. On the top left, using a yellow background, you can see our back office solution. The back office allows internal teams to create new entities in the system, connect them together, define rules and test for them, and much more. On the top right, using a light blue color, you can see in a high level our page serving platform. We will speak about it in more details in a few moments. And down below, you can see event bus and parts of the data architecture. But I will let Aviem, our data architect, to do the further explanation about it later on. If we look at the back office and our serving platform, we can spot several similarities and several differences. The back office is used for offline manipulations, while the serving platform is used for real-time page serving in production. Users who are working in the back office read, write, and change entities within our systems. While in production, all the entities are being served mostly as read-only in order to be able to serve them as fast as possible. Latency is important for us, as each and every page of us is being ranked by Google Speed Score metrics, and we want to serve them as fast as possible. We chose to use MongoDB both for our back office and our production environment because we can store JSON documents pretty easily with MongoDB and serve them really fast via MongoDB cluster to all our users. So one interesting question is, how do we sync between both environments, between the back office and our production environment? Within our system, we have a publish process, which allows us to selectively copy entities from the back office to our production environment, thus creating a decoupling between both systems. And this is our first architecture rule, decoupling where you can. The decoupling allows us to develop the back office and the serving platform independently from each other. We even use different teams and complete different development lifecycle. The same entities which resides within the back office will be published to production database and serve as a read-only entities to the users. So you might be wondering what one needs in order to create a new entity. Well, each entity has behind the scene a back office service and a runtime service. One used for manipulation of the data and the other used for read-only access. As you can imagine, we have a large amount of such services. We have more than 30 types of microservices. So the benefit is clear: separation of concerns. Rule number 2. Each entity has its own service handling its CRUD operation and even maintaining its own collection in MongoDB. Is it optimal? Well, it's working for us and was great for us, but over time it also imposed a delay on our development lifecycle. So we introduce new type of entities which are created by schema and deployed automatically to both environments. They can be served from both systems, back office and production, without any need for restart of our services. These are simple composable entities built like Lego bricks, which support composition and inheritance. But that is not enough. We love decoupling, so we added another decoupling layer. We introduced Event Bus, which allows us to decouple events running from our system towards our data platform. It allows us to decouple between development teams, so we have a serving team and we have a data team. But all we have to do now is to agree on a contract, guidelines to assist us on how to transfer events from one system to the other. Aviem will speak about it in a few minutes. So where did we stop earlier? Joe arrived to the product comparison table in top 10 umbrella site using redirect from Google. And he arrived to our page serving engine. Our serving engine, internally codenamed Rapido, is a Node.js based server which allows us to compose dynamically React components coming from a set of microservices which query data stored within MongoDB, as we've seen earlier. The serving and rendering engine is being governed by a complex rule engine, one which allows us to declare large amount of business rules in each page on the system. It allows us to run numerous multivariant tests. This means, as I said earlier, that we have large amount of UI permutation. So for example, an elder person from the US who is watching our site via his cell phone will see different page than a young woman coming from the UK who is surfing our website with her desktop. And she will see a different page from a young kid coming from down under Australia watching the same page on his iPad. We render our React pages on the server side mostly, but not necessarily, as sometimes we want to incorporate client side. For example, in order to gather information from the user and assist him in defining the best product that we can fit for his needs. The React components use GraphQL queries in order to query our set of microservices. We used to have our own query language, which was developed a long time ago, before the formation of GraphQL standard, and today we are still moving more and more towards implementing industry standards. Lately, we added Apollo GraphQL Federation with gateway and schema validation capabilities. This allows us to easily evolve our system, extend the entities, and validate their correctness upon the development process, and of course, with integration to our continuous integration flow. The last part of our diagram is the rendering engine. This is the part which is in charge of rendering the React components. In the past, it was a part of our serving engine, but lately we extracted it to several microservices, actually rendering cluster, and this move improved greatly the stability of the system. It lowered the consumption of memory and added a very low latency to the wire. Why? Because both the services reside within the same VPC and the same region within AWS. This move also allows us to grow vertically and horizontally these services as needed. Here you can see the state of the rendering server prior to the change that we made, where the query is running as part of the main instance. And as you can see, queries for product, for example, goes directly to the product real-time service, RTS. And when taking out the queries using Apollo GraphQL Gateway, we started polling the GraphQL endpoint for each one of the RTS services. Using Apollo Schema Registry, which is an external SaaS solution made by Apollo, we can define rules, check schema changes made by developers, and deploy them to production GraphQL Gateway without a need to restart our services in order to capture the schema changes. The advantages of this move are endless, and here are a few of them. We can now query for the performance of our queries and dig down, for example, why did a query took 30 milliseconds to finish. We can get down to the granularity of the items themselves and understand why it took so much time in order to retrieve them from the MongoDB server. As I said earlier, latency is important for us, and now we can look at latency over time in order to understand if a query goes beyond what we already had, say, a week ago or 2 weeks ago, and if there is a performance issue, let's alert the teams in order to investigate it. With the assistance of the tool, now it's really easy to write your own queries without even the need of a development environment. But the most important benefit is the ability to check for consistency. Getting alerts, for example, if someone changed the schema from integer to a string. We added it as part of our CI solution, and then if there is a change like this, it won't pass the changes over to the production environment. And another guard is the ability to check compatibility with previous production version. You can run it automatically with your CI solution and check every query or every change that you made over to the schema with past queries of the last month. So if, for example, you change something, it will run all the queries that ran over the past month on top of this service or this query in order to check that it's still valid. So before I give the stage to Aviem, in order to take you to the journey to our data platform, let me summarize a bit. Our CMS solution is based on React components stored within AWS S3 and rendered by Node.js-based server, Rapido. The server gets its data from Node.js and Nest.js microservices using GraphQL, and the services themselves are being deployed by Kubernetes to AWS and store the data from MongoDB clusters. The services source events also to Kafka and Kinesis database, and from there the events source towards our data platform. Some of the events source themselves towards AWS Neptune Graph database via dedicated Nest.js based microservices. As you can see, we have lots of technologies playing all together in order to compose our back office and service platform. And now the stage to Aviem to take you with a journey to our data platform.
Thank you, Ohad. Hello, everyone. My name is Aviem. I'm the data architect at NI. And what I would like to do now is take you through our data platform. So as we mentioned before, our system is split up into two parts. We have the back office and serving, and we have the data. Communication between these two parts of our system is done via an event bus. So what do our events look like? They are JSON events with certain headers that we require all our events to have. Specifically, we have an event header, which tells us what type of event it is, when it happened, and so forth. And we have a platform header, which tells us which one of our platforms produced this event. In addition to that, each event can define custom headers of their own, and we ask all events to put the payload of the event under a section called data. So we talked about our event bus. Our event bus is using Amazon's Kinesis messaging server, and it is multi-region. So since our deployment of our serving is multi-region, we have Kinesis in each region, and servers only need to produce events to the local Kinesis. From there, we have an event ingestion process, which reads all these events from all of the regions we're in to one central region where our data sits. From there, the events are poured into our data lake. So how does our event ingestion work? So again, we have Kinesis in multi-region. These raw events are read by Kafka Connect processes, which then write these events to another event bus in our central region, which uses Apache Kafka. These events are written to a raw topic, and from there they are processed by a streaming ETL using Apache Flink to process these events in near real time and validate them. So we validate upon the schema that they are the schema that we expect, that they are valid JSON, and other validations. Invalid events are written to an invalid topic, while valid events are stripped of any PII data that they have, which is personal identifying information data, which we don't want to keep for a long time. In addition, this data is encrypted on the server side, so we already receive it encrypted. We pour the PII data into a PII vault, where only applications that need access to this data will have access to this data. From there, the valid PII-free events are written to a valid topic in Kafka. And again, Kafka Connect reads these events and writes them to our data lake. So what is our data lake comprised of? We built our data lake on top of Amazon services, mainly Amazon S3 for our files to be stored in. This is Amazon's object storage service. And the metadata of our data that describes which databases and which tables we want that data to be presented as is stored in Amazon's data catalog called Glue, which is Apache Hive compliant, and therefore many data processing engines can use it. In addition to these, we also have proprietary repository of schemas that exist in our company. We use JSON schema to describe these schemas. And this project allows us to validate these schemas, allows to test with producers, and any changes to the schema is then reflected in our metadata with a CI/CD process. We created this internally because back then we didn't have a good solution for a JSON schema registry, but nothing prevents us from replacing this part with a schema registry in the future. Another part of our data is the analytics layer. So in order for our analysts to be able to create the reports they need to create upon our data, we first need to do some data processing. Up until now, we only talked about raw events. So what makes those raw events into the tables that our analysts are interested in is a series of ETL jobs written using Apache Spark and a proprietary project we started in our company called Liminol, which we will elaborate on later. And on our analytics layer, we have a Redshift data warehouse. This is Amazon's data warehouse offering, which can read directly from our data lake using its Spectrum component. And in addition to that, we have some ETLs which copy tables completely to Redshift for performance considerations. Our analysts use a third-party service called Tableau to create their reports, and Tableau extracts data from our data warehouse to their servers. In addition to our ETLs, we have other applications which we call data apps, which are apps that are in charge of writing our data to third parties and writing data into our data lake from third parties. So example of such data is bids, which we read and write from our different channels, Facebook, Google, Bing. We have conversions and revenue from our partners. So some partners can work server to server and send conversions directly to our servers. And others have different sorts of integrations. And for this, we use another third-party solution called Boomi, which allows non-developers to define various types of integrations without needing to code anything. So they can define integrations with our partners to retrieve conversions and revenue data from them. And all this conversions and revenue data is written from our data apps to the data lake. Basically, we have ETLs which copy data from applicative databases for these apps to our data lake. Other types of data we have is business entities, which are managed on Salesforce by our business side of the company. And we have our event ingestion, which we mentioned before. Another key part of our data processes have to do with data science. We make real-time decisions with automated models in production. We do this by training over 100 models daily. We have production-grade real-time inference, which is used by our serving platform and our websites. We implemented ML algorithms for ranking and personalization with constraints, which allow us to give our users a better experience catered to them. And we also have a Bayesian statistical model trained for A/B tests. And this allows us to run thousands of A/B tests in production and have their results come in quicker than they would have otherwise. So we use all these models to provide a personalized experience to our visitors and optimize quality and for conversions. So how does our data science layer work? We have model training pipelines running in our data region, again, using Liminol. They read data from our data lake, train models upon that data, which they then write to a model store that we modeled on top of S3. And from there, we have real-time servers which read these trained models and make them available to other services for real-time inference via HTTP, again, using our Liminol project, which we will talk about now. So we mentioned Liminol several times in this presentation. So what is Liminol? Liminol is our way to allow data scientists and data engineers to create data systems which are production grade and deploy their code to production while masking away from these users any parts of the stack which they don't need to have an expertise of. So we're talking about Docker and Kubernetes and Apache Airflow and EMR and more technologies that they shouldn't be experts in. They are experts in their problem domain. So how do we accomplish this with Liminal? Well, all we ask of our users is to add one file to their code repository, which is a YAML file we call Liminal YAML, in which they define their data systems. When they commit to GitHub, our CI process then triggers a job on Jenkins, which we use for CI. There we have Liminal installed, which does the heavy lifting for the user in the areas of building code, building images out of their code, and building services out of their code. So when we say services, we mean Docker image that starts a server, say an HTTP server, which allows services in our company access to a user's code without that user having to know how to create such a service. From there, these artifacts are deployed by Jenkins to our repositories. So images are uploaded to Docker Hub, and jars with Java code for ETL processes are uploaded to Amazon S3. Deployment of applications is then done to our runtime, which consists of Apache Airflow for scheduled data pipelines, Kubernetes to run user code and services, and Amazon's Elastic MapReduce to run big data jobs. So what Jenkins does is all services defined by the user are deployed as services in Kubernetes, which are constantly running. And their Liminal YAML file is deployed to Apache Airflow, where we also have Liminal installed. And what Liminal does there is it reads those YAML files and registers pipelines defined in them as Airflow DAGs, again, without the user having to need to know how to do this. Data pipelines that run our Airflow perform different tasks, and major tasks are launching pods on Kubernetes to run user code and submitting jobs to EMR to run big data jobs. There's one more layer as far as our SDLC goes, and it's monitoring. So for monitoring, we use various solutions. We have Datadog to monitor our services using their Datadog agent and APM to monitor services. So we report metrics with an agent installed on all our Kubernetes pods to Datadog. In addition to that, for all our data pipelines, Liminal automatically reports metrics and registers alerts to Amazon CloudWatch, reports metrics to InfluxDB, and generates automatically dashboards and alerts on Grafana. Again, without the user having to know any of this, they already get a monitored and alerted service running in production, as well as data pipelines. So we talked about this configuration file that we ask our users to create. So what does that look like? This is the anatomy of that file. So we have, for each data system, we have a name and an owner. We can define variables for reuse in the configuration. We can define images. So this is where we package the user's code as Docker images without them having to know anything about Docker. So types of images that we support are, for example, Java and Python for user code, where the user just needs to supply an image name, where in the repository the source is relatively, and if it's a language that requires compilation, a build command. Python, for example, doesn't require this last one. In addition to that, we have other image types, which are services, which we mentioned earlier, and our most popular one being Python server, which we mainly use for real-time inference for our ML models. Again, the user just needs to provide an image name, a type, where relatively in their repository the source code is, and they can define endpoints for this service. So we're talking about an HTTP Python server with HTTP endpoints that the user can then define. For example, here we have a my endpoint, which then invokes user code found in a specific model in their code and a specific function within that module that the user wishes for us to invoke in this endpoint. And that's it. That's all they need to know in order to create a service. And there is no complicated interface or anything they need to integrate into their code, but they just need to create a function that receives a string and returns a string, and that's it. The next section has to do with pipelines, where we define scheduled data pipelines, which are a set of tasks to be run sequentially. So for example, here we can see a pipeline with a certain allotted amount of time that it can run for before we cut it off. We have a start date, a schedule when this pipeline should be executed. This is a cron expression. And then we have a list of tasks that we want to run. Again, here we have several types of tasks, and a task is an extensible interface which allows us to develop more types of tasks and easily integrate them. So for example, here we have a task of type SQL, and SQL type is a type that we created to take a user's query and definition of an output table and an output path, and create from this query an ETL job running on Spark, which executes this query and outputs a table in our data lake without the user having to write any code other than this query. In addition, we have Spark task types, Java task types, which allow us to run Java user code as a pod in Kubernetes, Python task type, and more and more. We also mentioned services. So for services, there is no fancy configuration in the Liminol YAML so far. We only define a service name and an image. And we have another small YAML for our CI/CD process, which defines parameters for a Helm service to be run on Kubernetes. This is something we are also looking into incorporating into the configuration here to not have this other need of another file for configuration. And the last section, it has to do with monitoring, where the user can define metrics backends to which to send the metrics that Liminol automatically creates, which is application started, application succeeded, application failed, and application duration. We have several metrics backends, as well as alerts backends, which the user can define where to trigger alerts. Here we use Amazon's CloudWatch, so we define an ARM to trigger, in this case, SMS. And we automatically register alerts based on these metrics that we automatically produce. The alerts being application is not running on the schedule that we expect it to, application failed, or application duration was longer than the schedule allows. Here we see example of running Liminol on a local machine using Liminal CLI. So we have several commands. We have Liminal build, which builds Docker images from user code, Liminal deploy, which deploys a Liminal YAML to a local Liminal server, and Liminal start, which starts a local Liminal server. And when we say Liminal server, we essentially mean at this point an Apache Airflow server. In the future, there might be other implementations of the Liminal DSL that we find in the YAML that don't use Airflow, but for now, this is the only implementation that we have using Airflow. So what does a pipeline look like when it's running on Airflow as a DAG? It has a start where we send metrics that we send when application starts. Then we have the user's tasks. In this case, we have a training pipeline, which performs a train and a validate step, and an end task, which again reports metrics regarding the application ending. Here we see a request to a service created with Liminal that serves inference for a model trained on the iris dataset, which tries to determine if a flower is of the iris genus based on attributes of that flower. So here we send a request. In the body, we have a JSON with attributes of a flower, and in the response, the likelihood of that flower being an iris. server logs, for example, here we see a Python server's logs. So we use Flask to create the Python servers. We see an input from the request we just saw, some user logs, and the result returned. This project Liminal that we've talked about for the last few minutes is open source. We at NI believe in open source and believe in the Apache Software Foundation specifically, where a lot of the projects we use within our data platform lie, for example, Apache Kafka, Apache Airflow, Apache Spark, and the list goes on. And we approached the Apache Software Foundation with this project, which they deemed is a necessary project, which they do not have a solution for yet. And we were accepted into the Apache Incubator, where the project now is hosted and where we are trying to create a community to advance this project together. So we would like to invite you to join us at this effort. You can visit Liminol's website. You can visit the repository on github.com/Apache. And you can visit Apache's Jira server, where all issues for the project are documented, where you can assign issues to yourself to implement. We welcome any types of contributions and are eager to grow this community. So that's it. If we still have time remaining, we would like to field some questions from y'all. Thank you very much.